Hi everyone. So in this video, I'm going to go over the practice quiz 3 for the organic julep. All right. So it says identify the correct alcohol used in the Fischer esterification reaction below. Let's circle your answer. So Fischer esterification, as we'll talk about a few times on this practice quiz, is going to involve using an alcohol and a carboxylic acid. So an alcohol contains an OH and a carboxylic acid is a C double bond O bond OH. So when you look at the ester that is formed, so now we have C double bond O, and then an organic group, in this case CH, and then two methyl groups. So, and when we look at this, the carboxylic acid here is this carboxylic acid right here. The alcohol is this. And you don't need to know this for this question, but the oxygen actually comes from the alcohol, and then one of these OHs acts as the leaving group. So what we end up with is OH, so that's this O, and then we end up with this carbon right here, and then these two methyl groups right here. So our alcohol should look like this. So it should be 1, 2, 3 carbons with an OH in the middle, 2 propanol. Note that it's not drawn in the correct orientation, so it's basically just turned 90 degrees. So the answer here is choice letter D. Also note that it's not this one because it has the extra methyl group, which doesn't exist here. So if there's another methyl group here, that would be that one. And this one only has 2 carbons, and here you have 1, 2, 3 carbons. So it wouldn't be this one, and this one is just obviously wrong. All right, so this question says, a student completed the Fischer esterification reaction shown below by using excess carboxylic acid. So excess of this one, the carboxylic acid, this one's acetic acid, this stuff you'd find in vinegar. After the reaction, the product was worked up using liquid-liquid extraction procedures to remove the remaining carboxylic acid. A drying agent was used to remove the water from the organic layer, and then the ether, the organic layer, was dried up using evaporation. The following IR spectrum was obtained. So what we need to look at is the different distinguishing peaks of this IR spectrum, and then what it asks us is, does the IR collected support the conclusion that the product of the reaction is pure, i.e. it doesn't contain starting material. So if we look here, we have this broad peak around 3500-ish. This is going to be from your OH. If we look here, we have these peaks below 3000. So these are your CH from your aliphatic or your non-aromatic molecules. And then finally, we have this sharp peak around 1750, and this is your carbonyl, your C double bond O peaks. So we have OH, we have CH aliphatic, and we have carbonyl. Well, now what we need to look at is our functional material groups on our starting materials and our products, and see which one of these is distinguishing. So the first thing that I'm going to look at is the OH, even though it's the answer, because it comes first. But you could start on this end if you wanted. So if we look at the OH here, we'll notice that both of our starting materials have it. So our isopropanol and our acetic acid both have an OH group. So this OH likely comes from a starting material. It could also come from water, because water has an OH as well, but we did use a drying agent to remove the water, and this was in pure organic solvent, so chances are we got rid of any water that was there. So this OH likely came from the starting material. Since the OH came from the starting material, this means this is not very pure, because it does contain starting material because the OH came from the starting material. So the answer here is no. There's a broad OH peak around 3600 right here, which indicates that we have starting material present. What about the CH aliphatic? Well, this doesn't tell us much of anything, because if we look here, this has CH groups, this has a CH group, this has CH groups, so all the compounds have CH groups, so this doesn't tell us a lot about whether it's starting material or product. How about C double bond O? Similar. This has a carbonyl peak, and this has a carbonyl peak. So both starting materials and products have C double bond O. So this doesn't really tell us a lot. So here the indicative peak here is the OH, and the lack of OH would tell us that we have product, but the presence of OH tells us that we have starting material. Question 3 says, give the following fictitious reversible reaction, which will drive the reaction towards the reactant side. Circle your answer. So we have here this fictitious reaction, and what we're being asked about here really is Le Chatelier's principle. So in a nutshell, what Le Chatelier's principle tells us is the reaction wants to be at equilibrium. So if you do something to disturb the equilibrium, the reaction will do what it can to minimize said disturbance. So let's take a look. It says remove some B. So we have some B, which is a reactant, and we take some of the B away. So we lower the concentration of B. The reaction says, hey, there's not enough B in here. The only thing that the reaction could do to make more B is to react BC and A2C. So said another way, the only thing the reaction can do is shift to the left towards the reactants. So there's not enough B, the reaction shifts to the left to make more B. Add more A2. If you add more A2, the reaction says, hey, there's too much A2 in here. The only thing the reaction can do to get rid of A2 is to react it with B and C to form BC and A2C. So the only thing the reaction can do to get rid of this excess A2 is shift towards the products to get rid of some of this excess A2. Finally, remove some BC. Remove some BC, we lower this concentration. If we remove some BC, the reaction says, hey, there's not enough BC in the reaction. What does the reaction do to form more BC? Well, it reacts the A2, the B, and the 2C. Said another way, it shifts towards the products to form more BC because it doesn't have enough, because some has been removed. So these are the directions you'll shift. Then this says both A and C will drive the reaction to make more reactants. It asks us which one will drive it towards the reactants. So the only one that will drive it towards the reactants is to remove some B. The other two, as we discussed, will drive it towards the products. All right, number 4 says, in the first step of Fischer esterification, the carboxylic acid is protonated by a strong acid. Using acetic acid, this one's acetic acid, as carboxylic acid, draw the 3 resonance forms of the protonated acid. So I'm not going to try to squeeze them in over here. I'm just going to redraw my acetic acid over here. CH3, C double bond O, bond OH. So this is the same thing. This is a CH3, and this is, of course, a carbon. So I just redrew it over here. I was a little sloppy with my 3 there. But this is basically the same thing, and I'm just doing that so I have space. And what we're going to do is we're going to add some H+, okay? Probably sulfuric acid was used to catalyze this. So we're going to add a strong acid. So now we need to protonate. So if we look here at the resonance forms, okay, we have 2 lone pairs on this oxygen and actually 2 lone pairs on this oxygen. The carbons, this carbon is partially positive. It has no interest in an H+. This carbon is effectively neutral and it has no interest in an H+. But we could write a resonance form here where these lone pairs go up on here and this oxygen is minus and this carbon is plus. Because of that, we can write a resonance form with a minus charge on this oxygen is going to be the nucleophile. All right, it's the most nucleophilic thing in this molecule. So this oxygen is going to go ahead and grab that proton. And what we end up with is a CH3 bonded to a C, double bonded to an O, now with 1 lone pair, not 2, and an H. And this other OH is still going along for the ride, and I am going to explicitly write its lone pairs because they will be involved in the next part of the reaction. So if you look here, we have now this oxygen having 1, 2, 3 bonds and 1 lone pair. Said another way, it has a total of 1, 2, 3, 4, 5 electrons around it. It wants 6, it's missing an electron, so it has a positive charge. Now, it turns out that this can resonate in order to stabilize this. So one way in which this molecule can resonate is this lone pair can go up there. Or, excuse me, this double bond can form a lone pair up there on oxygen. So if we go to CH3, we have, my 3's aren't good here, C bond O, now with 2 lone pairs and an H, bonded to an O, still with 2 lone pairs, and an H. And I'm going to explicitly draw this bond in all of them so you can see it. Okay? Now let's look here. Right here we have 1, 2, 3 bonded carbon, which is positive. Okay, a carbon wants 4 valence electrons, it only has 1, 2, 3. It's missing an electron, so it's positive. So the plus charge moved over here. Effectively, we took an electron away from the carbon and put it onto the oxygen, and therefore the plus charge moved. Now, what else can happen? Well, this can resonate one final time. We can end up with this lone pair going here, and we get CH3, C double bond, O, now with one lone pair and an H. And up here, we have the oxygen with the 2 lone pairs and the H, and we get the third resonance form. Just like in this case, the oxygen with 3 bonds and 1 lone pair has a positive charge. So these are the 3 resonance forms of the protonated carboxylic acid. This carbon specifically, can then be attacked by the OH of the alcohol to go on and form the ester, because as we talked about previously, a carboxylic acid plus an alcohol yields an ester in the presence of a strong acid for a Fischer esterification. Alright, so the next 3 questions are all based on the same reaction. Okay, we have T-pentanol in the presence of ammonium chloride and ammonium bromide and sulfuric acid. And effectively, what we're going to do is we're going to brominate and chlorinate this molecule. Okay, so that's basically what we've got going on. In the first question, it asks us about the ratio when we have twice as much ammonium chloride as compared to ammonium bromide. In the second type of reaction, it asks us what the mechanism of the reaction is. And in the third one, it asks us for what is the compound that's formed in the first step of the mechanism. So kind of they're all the same. So what we need to do is look at the mechanism of this reaction. So what we have here is this, where these are all CH3s, that's a carbon, and it's an alcohol, so that's an OH. And we have in here NH4Cl, NH4Br. Okay, so we have chloride, Cl minus, and bromide ions. These are basically your nucleophiles. And we also have H2SO4. And at the end of the day, as you did in the lab, we're going to replace this OH with our 2 nucleophiles. We're going to get some of the chloro, we're going to get some of the bromo, and water is the byproduct of this reaction because this OH becomes water and leaves. So these are what we're going to effectively make. Now, what we need to look at to answer some of these questions is the mechanism. So let's take a look at the mechanism. So the first thing that's going to happen when we have this alcohol is OH is not a good leaving group. So the first thing that happens is protonation of this OH. We have a strong acid here. So the lone pair on this oxygen acts as a nucleophile. It attacks H+, which acts as the electrophile. And what we end up with is the protonated acid. Just like in the previous question, this oxygen now has 3 bonds and 1 lone pair. So it still has one of the lone pairs, okay? Has 2 bonds to hydrogen and 1 to carbon, so this is positively charged. Now, because this is a tertiary compound, the carbocation is stable enough to form. Water is a good leaving group, OH is not, so we protonate it, that's important. Now we have a good leaving group, and it can simply leave. And when it leaves, we end up with, this carbocation right here plus water. And this carbocation, although stable enough to form, is not particularly stable, so it's going to want to react with whatever is available. Well, what's available? The nucleophiles here are your chloride and your bromide. So I'm going to call it X minus, okay? X minus is going to come in and get attached to the carbocation. And what you're going to end up with is this with a Cl plus this with a Br. So we're going to end up with the chloride and the bromide product because X minus is a mixture of chloride and bromide based on the way that the reaction was described. So what type of mechanism is this? Well, it turns out that this is an SN1 mechanism. And why is it SN1? Well, it's SN1 because the rate equals K concentration of the thing that forms the carbocation. Said another way, the slow step of this reaction is the formation of the carbocation. This step right here is slow, and this step right here is fast. The slow step of a reaction, as you'll recall from your kinetics, is the rate determining step. So rate equals K, concentration of this. Since there's only one chemical in the rate law, this is an SN1 reaction. Said another way, it does not depend on the strength of the nucleophile. It doesn't matter if you have chloride or bromide, and bromine's a better nucleophile in aqueous acidic media. All right, now that we've talked a lot about this, let's go through and answer the questions. Okay, so the first question asks us, in the chemical reaction below, 0.1 moles of the 2-methyl-2-propanol, this one, is reacted with 0.175 moles of the bromine and 0.0350 moles of the chlorine. So basically we have twice as much of the chlorine as we do of the bromine. So we have 2x of this and 1x of this, if you will. And then we add some sulfuric acid, all right, to protonate the alcohol, as we talked about before. What are the products of this reaction and their respective ratio? Well, in this case, we're going to end up with these two products of the reaction. What's their respective ratio? Well, if we started with 2 times as much chlorine, we should get 2 times as much of the chlorinated product. If we started with 1 times as much bromine, we should get 1x of this. So they should have a 2-to-1 ratio. Why is that? Because the nucleophile doesn't matter. Said another way, this will react with the first nucleophile that it bounces into. It has 2/3 chance, if you will, of bouncing into a chloride and 1 into a bromide. Why? Because there's twice as much of the chloride as compared to the bromide. So since the nucleophile is not in the rate law, it doesn't matter which the nucleophile is, and the ratio of the products should be the same as the ratio of the nucleophiles. So in this case, we should expect to get 2-bromo, 2-methylpropane, and 2-chloro, 2-methylpropane in a 1-to-2 relationship. We should have 1 of the bromo and 2 of the chloro because of the fact that the nucleophile is not in the rate law and therefore is not part of the strength of the nucleophile. Doesn't matter. Whatever their initial ratio is what we should get. Note that if you don't have an SN1 reaction, if you have an SN2 reaction, so if you had used, for example, this alcohol and you have an SN2 type of reaction, in this case the strength of the nucleophile will matter. And if you start with a 1-to-1 mixture, you may not end up with a 1-to-1 mixture. In fact, you most certainly will not. Okay, let's look at the next one. It says the reaction below proceeds through what type of mechanism? Well, we again have the tertiary alcohol with the sulfuric acid. If you have the tertiary alcohol, it's going to go through the carbocation intermediate, which is going to be the SN1 mechanism, as we talked about for several minutes. And it says in the first step of the reaction mechanism, for the reaction shown below, which is again the same one, in this case we just have the ammonium chloride, we don't have both, but it doesn't matter, which of the following is formed? So the first step of the mechanism is the protonation of the alcohol. So this OH grabs the proton, as we showed in the mechanism right here, and what you end up with is the protonated alcohol, in this case choice letter C. So these questions are all very related to each other and are based on the mechanism. It's important that you guys take a look at the mechanism of this reaction, which is gone over in the video for this reaction, because this one is fair game for the quiz as well. All right, last question. It says, a student completes a nucleophilic substitution reaction using similar procedures of the ones used in the experiment performed in the course. The reaction conditions include equal molar mixture of the bromide and the chloride nucleophiles. The reaction is shown below with the relative physical property data. The student isolates a mixture of the alkyl halide products in pentane and analyzes the sample using gas chromatography GC. The GC results are included below. The first thing it says is label the chromatogram below with the alkyl halide products. Briefly explain the reasoning for the identification of the peaks. So here we have the 2 alkyl halide products. This one is the 1-chloro product, and this one is the 1-bromo product. This is because GC separates things by their boiling point. So this one has a lower boiling point, it will have a lower retention time. This one has a higher boiling point, it will have a longer retention time. Remember, this is literally the amount of time, retention time, that it takes to go through the column. The lower the boiling point, the shorter amount of time it will take to go through the column, and vice versa. Why this has a lower boiling point is because it has lower dispersion forces. Chlorine is smaller than bromine, so this is going to have stronger dispersion forces and therefore higher boiling point. Not sure you need to include that because the boiling points are given, but that would be the reason for that. Also notice, as we talked about in the previous question, in this case we have one butanol. So in this case, we end up with, even though we start with an equal amount of chlorine and bromine, we end up with more of the bromine and less of the chlorine. This is because this undergoes an SN2 mechanism, okay? And when it undergoes an SN2 mechanism, the strength of the nucleophile matters, and in aqueous acidic media, the bromine is a better nucleophile. This is exactly what you did in the lab. So it says, which I already pretty much answered, write the rate law for the nucleophilic substitution reaction performed by the student. The GC results above are the GC results above consistent with the expected ratio of products for nucleophilic substitution reaction performed? Why or why not? Be sure to reference the GC results clearly in your explanation. So this reaction is undergoing an SN2 type of reaction. Okay, so you're going to end up with starting with the protonation of this, and then the nucleophile is going to come in, and you're going to end up with the transition state where the water is leaving and the nucleophile is coming in. Bromine is a better nucleophile than is chlorine, so we end up with more bromine, larger peak area percentage, and less chlorine, smaller peak area percentage. I mean, it's obvious just by looking at them. This peak is bigger than this peak. So even though we started with an equal amount of this, we ended up with more bromo product because it forms faster. We could say the rate equals K, concentration of the protonated alcohol, times the concentration of the X minus, where X minus equals Br minus and Cl minus. Okay, so these are your bromine and your chlorine, and they're actually in the rate law. This is why, even though we started with a 1-to-1 mixture, we end up with more of the bromo product. Again, as I mentioned in the previous question, there's a lot more detail on this particular reaction and its mechanism in the video for this reaction. And the SN2 reaction, or the 1 alcohol, in this case 1 butanol, are fair game. So just be aware of that. I went over the mechanism for the T product, okay, this one, in the previous questions. All right, thanks for watching the video, and I hope you found this helpful. Keep up the hard work. You guys are doing awesome.